Hi, my name is Bernard Brault. I'm with OTN Systems. Today I want to do an application note video, and it's about XTran interoperability with TDM legacy networks such as T1 primary mux or channel bank and SONET systems and so on. So what I have here on the slide is XTran network, shown here represented by these three XTran nodes. This could be a 1 or 10 gig MPLS, and it could be mesh. So we have on the access side, we have two Schweitzer relays, and at the far end we have the corresponding relays point to point over a T1 channel bank. So just to show you what this looks like, as shown here on the next slide. So we got a C3794 current differential relay, which could be a 311, 411L, and they basically are mapped over a T1 in one channel, and then the mirrored bit application is mapped over a different channel. And as you know, the T1 can handle up to 24 channels, so we could have 20 some remote sites here on the XTran carrying mirrored bits in C3794, and then mapping those into, the various relays, corresponding relays over this T1 link that we have right there. Another similar application, or one of the reasons why you may have this, is that you may have a T1 radio system, 4 or 8 T1, and at the remote end of this T1 radio system is a T1MX or a loop channel bank, and then you want to have like some channels between the XTran network and then the remote. Keep in mind that this, instead of mirrored bits, could be an RTU, for example. Another similar application to this might be a SONET ring, where you may have a jungle mux SONET ring, OC3, 12, or 48. Again, something very similar to what I shown before. Between the XTran and the jungle mux would be a T1. The T1 would be provided by JMUX over a CDAX module, and then the CDAX can actually map different channels to different remote locations. So between these two mirrored bits right there, and then between these two C3794. So we could do the same thing on the XTran and map these over to T1 and then interface it right there. So one of the first thing you'll notice is mirrored bits is a serial protocol, and there's no interoperability between serial mapping between different primary mux or channel banks. There was no standard for it, so every different vendor implemented it in their own way. So one of the way out of it is basically to convert anything serial into C3794. And it so happens that Schweitzer has this device, which is a serial to C37 converter. It's a very nice, convenient little device. Part of the reason is because it'll take power directly from the receive pin, and it'll draw very little amount of power, something in the order of about 20, 30, 100 milliwatt or so. It draws about 20 milliamp, and pretty much all serial ports can power up to see the converter. It only takes a receive transmit. I believe the request is send, clear to send, or loop back, but basically it takes the transmit and receive and ground pin. Those are the three necessary pins, and then you go over a C3794, and that's what's used for conversion. Notice that here I have some specs about it, and it goes 300 to 19.2. Even though it's converted to 64 kilobits, it doesn't handle baud rate higher than 19.2, but usually that's sufficient for most RTU and mirrored bits application. The other thing that's interesting to notice here is the temperature range. So this little device here can operate between -40 to +85 degrees Celsius. So a very nice and convenient way of converting anything serial into C3794. So if I go back to this application here, in fact the mirrored bit is done over one of these small converter into C3794. So we have a few customers are actually doing this, and they have quite an interest in this application. So decided that I was gonna like talk about it and then also do some testing over it. I want to talk a little bit about the test that I'm going to be conducting. So here's the lab setup that I'm going to have. So I have a instead of the 311L in my lab, I have a DTT transfer trip module that goes over C3794. So I'll be injecting transfer trips into this DTT Schweitzer module, and they'll be sent across one channel over a T1, and then back into another XTran network down here into the remote DTT module. And the C37 converters there are going to have another separate channel over the T1, and this one is going to be connected to a mirrored bit tester, and I'll be able to look at the latency in both direction, injecting traffic in both direction, measuring asymmetrical delay, measuring packet loss, and so on. I could do some further testing by doing hitless switching between these between the T1 and the C37 and so on, but so that's going to be the test setup. Notice that the two XTran network that you see right there are not connected via MPLS. There's not going to be any MPLS, so I'm going to have two entry points between the TakeScare NMS, one entry point into this network, another entry point into that network. Normally in the real life application, if I go back to the real life application, I would have to create two tunnels, one tunnel point to point between this remote end and this sort of aggregation T1 point, and then I'd have a separate MPLS tunnel for point to point from here to here. Those could be hitless or they could be protected. And finally I would be attaching two separate service, one service over one T1 channel, a second service over a second T1 channel. In the case of my lab setup, I have to do the same thing on the far end here. So basically take the C37, map it into a channel there, but also take a channel, the same channel there, and map it to the C37, and then put a cable in between these two and see if everything works as shown here. Alright, so let me do a pause, and then what I'm going to do is I'm going to show you how to configure this over TakeScare. Hi, we're back, and this time I'm showing a TakeScare client, and I want to show you how we're going to provision the C37 over T1 on different channels. So I have the TakeScare client started, more specifically on the connection tab, and what I see here is two independent XTran network, meaning that they are not MPLS connected, so there's no DCN channel between the two, and so I have two entry points, one entry point into node number 4 in order to manage this 3-node network, and I have a second entry point into node 31 to manage the network at the 3 nodes down there. And what we want to do is we want to create a C37 service between 3010 and a T1 here, channel 1, and that's going to carry the first application. The second application is going to be between node number 6 and that same T1 in node number 4, except it's going to be using channel number 2. Normally that would be sufficient, and we'd be handing off that T1 to a TDM network like I've shown before, either a Jungle Mux Sonnet network or a T1MX or a loop channel bank. But in the case of the lab setup here, what I'm going to do is have something symmetrical down here, and I'm going to pass the T1 to the second XTran network, where I'm going to take the first channel and map it to node number 5 down there, and take the second T1 channel from 31 and map it to 1004. So effectively by doing this, I'm connecting a C37 application here, which is going to be a transfer trip Schweitzer DTT application across here and back down to node number 5, and the second application going over the Schweitzer mirrored bit serial converters between node number 6 and 1004, and between these two serial converters I'm going to run a mirrored bit tester to see and monitor latency and so on. Alright, so I've created so far all the 4 tunnels, as you can see. So I need, in order to actually create the service, I need to have a tunnel. So the first one is going to be a C3794 between this site and the node number 4 over channel number 1. So I'm going to use this 1-1 tunnel. This is a 1-2 tunnel between these 2 sites, and the network down there I'm going to have the same thing down there for the first application, and this one for the second application. So the interesting part now is to create these services. So I'm gonna go ahead and show you how to create one of the service, and then I'll do a pause. So let's create the C3711, and it is a C37 application, so it's circuit emulation, and I select C3794. Notice it's saying setup, means like a full T1. In this case, I want to do fractional T1, just one channel, setup. In the case of JMUX, the term sometimes is called N times 64, N being 1 to 12. It's something very similar here, except now the N is going to be 1 64 kilobit channel, and the next step is going to ask for different ports. So in the 3010, I'm going to pick the C37 port number 1, which is an optical port, and it's a C37 port. And on node number 4, this time what I'm going to do is I'm going to pick a T1 port. This C37 card has 2 C37, the first 2 ports. Port number 3 and 4 are T1s. I'm going to pick this T1, and it's asking me what channel I want to drop the C37 on. And because I'm selected this card as a T1 card, I have this option of channel number 1 to 24 that are currently available. If this was an E1, it'd be all the way up to 30 channels. So I'm going to pick channel number 1. Now it's asking me for a tunnel, so we're going to pick the first tunnel, and the circuit emulation parameter is a short haul link, less than 200 meter. I'm going to make this 3 and a de-jitter buffer of 2 milliseconds, and it's got a predicted delay of 1.7 millisecond plus fiber delay. So we'll be able to measure that later while using the tester. So I'm going to click on next, and we're going to make this a top priority, and we're done right here. So if you look here, right, so this is a summary, and done creating the first service. So if you look here, services C3711 is between node 3010 and node 4, and more specifically you can see here it's interface 4 port 1 to interface 9 port 3, channel number 1. So I'm going to make a pause, create the other ones, and then we'll talk a little bit about timing and clocking. Okay, so we're back. So I created all 4 services. So on the top network, I have the C37 between this and channel number 1, and you can see here on node number 4 it's dropping on channel 1, versus the second one here between 6 and 4 at node number 4, it's dropping on the same port, the T1, except it's dropping on channel number 2, and that's what's shown down here. And I have the corresponding setup on the second network. So here's the this one. So this application is going to take on node number 31, as you can see, picking up channel number 1, and finally on the last one in node number 31 right there, channel number 2, dropping into 1004. So just want to talk briefly about a little bit about timing, because we're dealing with the TDM. So on the next couple of slides I'll come back and discuss timing. Okay, let's talk a little bit about timing. So in this network, for example, we would be taking the timing from the Sonnet side. So the T1 port on the XTran here would actually be clocked from the JungleMux CDAX card, T1 right there. So this would be timed externally, so it would take external timing, and the remote ends are always adaptive, so they will basically, you know, recover clock from the MPLS network. And our In this case, what we have is this network. So what I'm going to do is set this to internal timing as if it was a JMUX, for example. This one will be externally timed, and all the remote devices right there, or remote ports, are going to be adaptive clocking, and I'll show you how to do this in TXCare. Okay, so we're back in TXCare, and what I'm looking at now is the T1 port, one end on the node 4 and the other one in the other node. And what I have to do is set this one to internal clock and set the other one to receive. And